Job 1, constant velocity motion. I made an observation of a video of my friend moving her hand across the screen. I modeled it, the main result applying the momentum principle or Newton's second law, by setting F net equal to 0 to model good predictions of the observed motion. Here's the clip of my friend moving her hand. I used the first frame to set the origin at the tip of my friend's thumb. I chose the x-axis and oriented it so that her hand would move in the positive x direction at a constant velocity. I took the center of her hand as the average position and marked it as shown on the screen. I used the diameter of her hand by using the calibration stick, set that as a length scale of the video, which I set as 0.1016 meters. The time length for the frame is about 1/30th of a second. The total clip time is around 1 second. The last frame was before her hand is completely stopped. To predict the motion, I needed the mass of her hand, which I took to be 0.45 kilograms. I used the initial position of the ball, which I got from the analysis of the first frame of the video. The average velocity I estimated by taking delta x over the entire video clip. That is the final position minus the initial position, and divided that by the total time of the video clip, which is about 1 second. That gave me the estimate of the initial velocity. Lastly, I chose delta t to be small compared to the 1 second time elapsed of 0.01 seconds. So I predicted for starting at time for about 2 seconds and applied Newton's second law, so the final velocity and constant velocity will be equal to the initial velocity, which means the second term, F net over m delta t, has to be equal to 0. The only way for that to happen is to have F net equal to 0. I set F net equal to 0 in the model and then used that to predict the motion based on the given initial condition and system mass. Notice that the system mass doesn't come into play because if the F net is 0, then the mass does not matter. The visualization, here's a visualization of her hand. The origin is here, which the ball we are going to consider as a hand goes to the right, and the graph shows that. It starts at the origin, going from the positive x and continues to get more positive. The best way to compare the model and the experiment is to plot both the data and the predictions on the same graph. So this is the x position versus time. X is in meters, time is in seconds. The blue represents the experiment, the black line represents the model. The model line tracks the line of blue diamonds, so we can call this a good agreement between the model and the experiment. For the what if question, what if I made the choice of origin in a different place? How would my results change? What if I chose the hand going to the right in the negative x direction? So in the model, the only changes would be the hand position and the hand velocity would change to the negative. The ball's motion should look the same. The ball should be still moving in the right direction, but the graph should look different. The graph goes in the negative direction and continues to go in the negative direction as time advances. However, in this screen, it doesn't, but it should. It's going in the negative direction, but instead it's going to the left. Instead, the ball should be still going to the right in the negative direction. Finally, what does it mean to start with the v constant we found? What does it mean? We start with the v constant we found by setting F net equal to 0, which are the total pushes and pulls are 0, we got a good fit. This results that if F net is not 0, then the velocity would not be constant. That is, the object would speed up or slow down or change directions. In the model, the only thing that should change would be the F net. The F net would not be 0. Instead, it has numbers. Here's the model showing the change in direction and velocity.
Now we're going to step through the same lab report and show you what the experts thought about it. Keep these critiques in mind when you start to plan your own video lab report.
Modeled it. The main result applying the momentum principle or Newton's second law by setting F net equal to 0 to model good predictions of the observed motion.
Another very good introduction. The main result here is that setting the net force equal to 0 in the computer model results in constant velocity motion, and the speaker makes that clear.
Notice that the system mass doesn't come into play because if the F net is 0, then the mass does not matter.
This is a very good observation about the physics. The mass doesn't matter when the net force is 0. That's a good connection to make between the properties of the object and the motion of the object. The screencast format is a good choice for this video because the code features prominently, but the resolution of the video is too low to clearly make out the text.
Here's a visualization of her hand.
Her model visualization shows the object moving from left to right, while her video shows her object, the friend's hand, moving from right to left. The problem here is that she didn't orient her model axes to point the positive x-axis to the left, consistent with her choice of axis that she made when she did her video analysis. She could fix this simply by rotating the visualization by right-clicking and dragging in the display window.
The model line tracks the line of blue diamonds, so we can call this a good agreement between the model and the experiment.
The physics here has a major problem. The model line has a different y-intercept than the experimental data. They should be the same because the initial position of the object in the observations should be used as one of the initial conditions in the computer model. However, there's a problem here that's worse than that. She doesn't even show the predictions of her computer model. Instead, she's just using a spreadsheet fitting function, and she's calling that her model. Simply drawing a line through data and citing quantities like r squared without any physics meaning does not help us understand and predict the observed motion. This is totally unacceptable. Let's take this as an important lesson. Let's make sure we focus on comparing our observations to the output of our computer models, which make predictions based on motion physics principles.
For the what if question, what if I made the choice of origin in a different place? How would my results change? What if I chose the hand going to the right in the negative x direction? So in the model, the only changes would be the hand position and the hand velocity would change to the negative. The ball's motion should look the same. The ball should be still moving in the right direction, but the graph should look different. The graph goes in the negative direction and continues to go in the negative direction as time advances. However, in this screen, it doesn't, but it should. It's going in the negative direction, but instead it's going to the left. Instead, the ball should be still going to the right in the negative direction.
Here's another issue. Changing the origin of the coordinate system and changing the orientation of the axes are two separate independent things, and the speaker is confusing those here. She mentions changing the origin, but acts like she's switching the orientation of her x-axis. She also has some confusion about exactly what happens when you change the orientation of the coordinate axes. In summary, this video has a good presentation, though the resolution should be a little higher, but some serious flaws in the physics. Since by far the most important part of the lab reports is the physics, this second video would receive a poorer evaluation than the first.